Alright, do some like chores right quick. Alright, let's make a try. So, yeah, I probably should have waited to start this. I know I did that wrong. Let's see. Alright. So today, I'm going to do these 3 problems. I'm going to read system design in a hurry. I'm going to work on Gleam. I'm going to study Kubernetes. Simple enough. So let's look at this. Try prefix tree. So this is probably going to be one that I just watched a video on. Insert word into the try. Search, return true if it's in there. Starts with, there's a previously inserted, there's a prefix. Topics are hash table, string, design, and try. So let's just watch a video on this while you eat breakfast. Let's go here. Shut up, oh my god. I'm gonna try prefix tree. Where's my cursor, dude? Oh my god. Leetcode try.
Code today. So today let's solve implement try, aka a prefix tree. So a try or a prefix tree is a special type of tree, and it's used to efficiently store strings, and the applications are some stuff like autocomplete and spell checker. The reason is because the prefix tree allows you to efficiently filter and search based on prefixes. So let's look at the actual implementation of it. So we're going to have a object. That's what we're going to be doing this time, a try object. And our job is to fill in 3 functions. The first function is going to be inserting a word into the try. The second function is going to be searching for a word in the try to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the 3 functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a try actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the try, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just added it, so of course we're going to return true, apple exists. Then we're going to check, does the word app exist? It does not. The word app does not exist. And third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a try is. And in this problem, they told us that the limitation is that the words are going to only have characters from lowercase a to z, right? So this is lowercase a to z. So that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say a, insert it, P, insert it, second P, keep doing that, and every time we're inserting a new character, we're going to add it as a child of the previous character. So we inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP. But we know we actually did apple, right? Full on apple. This is the last character. So we mark here as the last character. We are marking it even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters, but it's considered the root, right? And so we're going to check, does this root have the child of the first character that we're looking for, right? So take a look. This because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters, but it's considered the root, right? And so we're going to check, does this root have the child of the first character that we're looking for, right? So take a look. This is the word we're looking for. Obviously, we're looking for the character A. So we check, hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right, as a child. So next character P, does this have a child P? Yes, it does. Next character L, we have a child L. Next character E, this is the last character, so we do have an E over here, right? And last thing that we have to confirm is, okay, this is the last character. Is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because apple does exist in the try. So next, let's run search again. And this time, let's check if a word app exists inside of our try. App, right? Not apple. So obviously we know that starting from the root again, we do have a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, A, P, P, shouldn't this function return true? No, we're not returning true, and the reason is this node is the last character of the word, right, P, and it's not marked blue, meaning it's not marked as a word, right? Remember, we only inserted apple into our try, right, into our tree, and we marked this as the end of the word. We never inserted app into the tree, so this is not marked as the end of the word. So we return false for saying that app does not exist in our tree. App is not a word yet. Next, let's run another function on our tree or try. We're going to check, does a word start with app? How can we check if a word starts with app? Well, we're basically running the exact same thing what we've done, right? We're starting at the root. We're going to check character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them. Start at A exists. Check P exists. check another P, P does exist. So since we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right? We never inserted app, or we're guaranteed that there is some word below that has been marked, right? Because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right? There definitely exists a word that starts with app, right? And so this starts with function is the main reason we're even implementing a try in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we could just use a hash map for that, right? Because hash maps can, or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? APE. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say APE and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child. And would it take one word? So a prefix tree. Prefixes can be checked very efficiently. So now let's actually jump into the code. All three of the functions, insert, search, and starts with, are pretty similar functions. So even though we're going to write a lot of code, it's going to be mostly similar. So let's jump into that. So our job is to implement a try, but we can't really do that without implementing a try node. So the first thing I'm going to do is create a try node, and all we're going to do is just create the constructor. So in Python, that's what I'm doing. And
So yeah, I'm gonna just try to write this. So you need you kind of need a node here. This will have a children. We'll have a car val. The tribe will have a head. This can just be a dummy. Equals, you can also have a constructor in here. Node. Val. Dude, I hate not having Vim motions. You're gonna have val. Children. Or we can just do children. That's fine. Yeah, I think it's already instantiated, so that's fine. Head equals new node. Can just have the val be zero, character 0. So when you make this, do nothing. Insert. So when you insert a word, car by car. So you're going to start it. Let's just watch
Net
one.
is basically the constructor, and I'm just going to have a couple of member variables for this. So we are going to have children of a trie node, right? It could have children. It could have 26 children, but instead of doing an array, I'm just going to do a hash map because that's easier. And remember, we can also mark every
Hash map.
single node as if it was the end of a word. I'm going to say
Yeah, I kind of agree with that actually.
end of word is
Yeah.
going to be a variable. Initially, it's going to be false, but we could set it to true if the character was the end of a word. Notice how we're not actually storing the character itself in the trie node. That's going to be implicit from the hash map, from this hash map. So if we were adding a, let's say a character A, a lowercase character A, we would say the children, we would say children, for character A is the key, and we're going to create a new trie node for that character A, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire trie node class. Now let's actually get into the trie class. So the first thing we're going to do is initialize.
It doesn't need a value.
This, so let's get rid of this comment, and for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root trie node, and that's it. That's all we're going to do for the constructor. And once the trie node is created, we basically have an empty tree. Even though we have a root, it's empty because it does have
Yeah, I see it now. This because the car is encoded here. I have a node pointer.
it does not have any children, so we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize ourselves. Current is going to be set to the root, so we're going to initially start at the root, right? And then we're going to go character by character in the word. And for every single character, we're just going to check two things. Does this character already exist? If it doesn't already exist, so if this character is not in the current nodes dot children hash map, right? So if this character is not in our hash map yet, that means it hasn't been inserted yet. So what are we going to do? We're going to create a try node for this character. So cur dot children, and the key value we're going to use is the character, and then we're going to create a new try node. So this is how we are going to be inserting characters. To children, we're going to use the character as a key value, and then we're going to create a empty try node. And we're only doing that if the character doesn't already exist. If it does already exist, then we can skip that step and just say that current is going to be set to that child, right? So if that character already existed, then we can just update cur and move to that character and then continue our for loop, right? So we're going to do this for every character in the word. And then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something, the characters already exist, or we just created them. Now current is set to the last character of the word. So what are we going to do to current? Well, we're going to mark it as the end of a word. So we're going to set end of word equal to true now, and then we don't really have to return anything. So that was pretty simple, right? Not a lot of complex code. We did have to
that's kind of smart.
go through every character, and we either created nodes or
So for each C in the word, if it's not in the current children,
just iterated through those nodes. And the remaining two functions, search and starts with, are actually going to be very similar to this insert function. So now let's get started on search. So we want to search to determine if a word exists or not. So just like the previous function, we're going to start at the root node, so self.root, and we're going to go character by character in the word, and we're going to check if this character exists in our tree. If it does not, so if C not in current.children, if this character does not exist, then what do we have to do? We return false, meaning the word just simply does not exist. If it does, then we can move ourselves to that child node. So we can update cur and set it to the child node of that character. And then we're going to basically keep doing this for every character in the word. If the word doesn't exist, we'll return false. If the word does exist, that means the entire loop will execute, and then then cur will be the last character of the word, and we know that it is a word if cur has the end of word variable set to true. So this is the variable we're going to be returning. If this is set to true, that means this is a word and will return true. If it's set to false, that means it's not a word and our function is ultimately going to return false. And now, last but not least, let's get started with the starts with function. And this function is actually going to be the exact same as the search function, except we're not going to have to determine if it's the end of a word or not, right? We're not checking if it is a word, right? We are just given a prefix, and we just want to know if there's any word that starts with this prefix. So once again, for the third time, we're going to be starting at the root, and we're going to go character by character in the prefix this time, right? We're not given a word this time. And if this character is not in our tree, so if it's not in the children right now, then we will return false, meaning the prefix does not exist, therefore no words start with this prefix. Otherwise, we will shift our current pointer to that child pointer of this character and continue on. And at the end, if we do reach cur, then we can immediately return true because we know that there's at least one word that starts with this prefix. We don't have to determine that the prefix itself is a word. So that is the entire code.
Alright, I think I understand it. Let's do it. Dude, oh my gosh. How do people actually use arrow keys? Let's do a struct. Try. We can call it a try node. Try node. This will have what? So we have an unordered map of car to try node pointers children. Boolean is end. When you create this, you can just have here a head. We can add. Sorry. Try node pointer head is equal to constructor here. Try node. Its end. Its end. Its end. Try node ahead is equal to a try node. False. Actually, we can just do this. So that kind of does our constructor for us. Insert. So what you do, start at the top, so cur is equal to head. For the characters in the string, for car C in string.cars. Why is the indentation off? Either way. For car C, if her dot children dot find C is not equal to her dot children dot end, then we need to add it. So that involves doing cur dot children of C equals, so we need a new node. New node cur equals so new node equals new node new node new node, and then you just need to make the end, so cur dot, we're gonna do this, cur dot is end is true. Yeah, it makes sense. So how do you search? So you're gonna start with a head. Node cur is equal to head. So for car scenes, sorry, word.cars. For car scene word.cars. If, so it's really just the same thing. Except if credit children define C is not equal to end. Cur is equal to cur dot children, sorry, cur children dot find cur children of C. Let's do this. If it is equal, and then you do this. You do this. Starts with, it's the same thing. Except here you have to do, you need to search, you have to do cur.is and here you just do true. Try node to try node pointer. Node, let's just rename it node. Remember cars. CPP stir to cars. Or CNS. So it's just not a pointer, it appears. Then you just do this. New node. Cars. Is end. Yeah, this should be a arrow. Word prefix. Wrong answer. So insert Apple. So do nothing. Insert Apple. Search Apple, returning false. Machine word, if could have found is good to dead end. See if key in unordered. Contains, that's just way better. No pointer. So I think it means this function still works though. If cur children contains. So head is null. Start at the head for the characters if it contains it. So this is incorrect. If it doesn't contain it, you do this. If it does, you just do cur equals cur children C. So we're still returning false here. Yeah, this is the other way. And this is also the other way around. Next. Fizzbuzz. Okay. If n% 3 is equal to 0 and n% 5 is return or print? So it wants to build it back, so vector string ants dot push back fizz buzz else if n%3 is equal to 0 ants dot push back fizz else if n% 5 is equal to 0 it's a push back buzz else ants dot push back and 2 I think it's actually 2 string event right 3 and oh yeah, so you gotta do 4 int I equals 0. Wow, that's actually really dumb. I'm actually chopped. I'm cooked. I'm actually cooked. I'm cooked. Oh my gosh, I'm so cooked. No. It's over. It's over. I should give up. Why are we saying fizzbuzz in the beginning? Okay. That's what he said. I'm curious if there's some like over-engineered. So there's a better approach. Indent this, bud. What are you doing, man? Что ты делаешь, брат? Alright, so I might pause this one. So I'm satisfied with those two. I mean, the fizzbuzz was more just so I don't get cooked. Let's see. I'm gonna pause on this one and do system design in a hurry. So I already read this part. Next, that's how to prepare. What does it skip? How to prepare? Delivery framework. All right. Let me go to the bathroom real quick. All right. The easiest way to sabotage your chances of getting an offer is to fail to deliver a working system. So you want a structure. Requirements. So you just want to get a clear understanding of the system that you're being asked to design. Break your requirements into two sections. Functional requirements. Users should be able to. Core features, first thing you discuss. It's a back and forth with your interviewer. Targeted questions if you were talking to a client. Does the system need to do X? What would happen if Y? You're designing a system like Twitter. Users should be able to post tweets. Users should be able to follow other users, and users should be able to see tweets from users they follow. A cache might have the requirements like cache. Client should be able to insert items, set expirations, read items. Focus on what matters. Non-functional requirements. The system should be able to. Okay. Should be highly available. So highly available. Prioritizing availability over consistency. $100 million DAUs. A DAU is a daily user. Huh? DAU is a daily user access. Huh? Okay. Users. Low latency. Render a feed in under 200 ms. CAP theorem. Should your system prioritize consistency or availability? Note, partition tolerance is a given. What is the P? Partition tolerance. That makes sense. The system continues to function even when no partitions. Availability. Every request gets a response, but maybe not the latest one. All nodes display identical data. Chain reads and writes. Environment constraints. Limited battery life. Limited memory bandwidth. Limited memory or limited bandwidth. Scalability. All systems need to scale, but does the system have unique scaling requirements? Does it have a bursty traffic at specific time of day? Are there events like holidays that will cause a significant increase in traffic? Consider the read versus write ratio. Reads or writes? Latency. How quickly does the system need to respond to user requests? Specifically, consider any requests that require meaningful computation. Low latency search when designing Yelp. Durability. The data is not lost. Social network, you can lose data. Banking system can't. Okay. How secure does the system need to be? Data protection, access control, regulations, compliance. Fault tolerance. How well does the system need to handle failures? Redundancy, failover, recovery mechanisms, compliance. Data protection laws. Capacity estimation. Many guides you'll read will suggest often doing back of the envelope calculations, often unnecessary. Imagine you were designing a top case system for trending topics in Facebook posts. You'd want to estimate the number of topics you would expect to see. What is a top K system? Very large stream of videos on YouTube. The top K most, okay. The top K most trending topics in Facebook posts. I want to estimate the number of topics you'd expect to see. This will influence whether you use a single instance of a data structure like a min heap, or if you need to shard it across multiple instances. Which will have a big impact on your design. Okay, core entities for 2 minutes. Core entities of your system. Define terms, understand the central data. Data central to your design. Gives you a foundation. Bulleted list. One sec. This guy's goated, dude. This guy's goated. No, that'd be good. All right, one sec. Let me get something to drink. All right. So back to the example of Twitter. Core entities are users, tweets, and follows. Dang, that's a even within the blog post, this guy's just going crazy, man. It's kind of pleasant. Huh, domain specific language. Ooh, this is the book. Yeah, but this also reminds me I can kind of write a better name for what this is, what request is. It is more of like a DSL curl. Repeatable HTTP requests. A domain-specific language for repeatable HTTP requests. I feel like that's solid. I don't know. Whatever you want to call it. Get back to this. Contract between your system and its users. RESTful GraphQL. Wire. Data flow. Data processing systems can be helpful to describe the high-level sequence of actions or processes that the system performs on the inputs. Data flow. For a web crawler, this might look like fetch seed URLs, parse HTML, extract URLs, store data, repeat. High-level design. You have a clear understanding of the requirements, entities, and API of your system, you can start to design the high-level architecture. This consists of drawing boxes and arrows to represent the different components of your system and how they interact. Yeah. Servers, databases, caches, etc. Key technologies will help you know what you need to know. Ask your recruiter what software you'll be using for your interview and practice with it ahead of time. I mean, that's a little cringe. Don't overthink this. Your primary goal is to design an architecture that satisfies the API you've designed, and thus the requirements you've identified. So this guy's suggesting going through each endpoint. I actually kind of like that a bit. From what I've seen in like other example systems design interviews, never really heard somebody going into the endpoints. That is curious. It's incredibly common to start layering on complexity to already never a complete solution. Focus on relatively simple design that meets the core functional requirements. As you're drawing your design, you should be talking through your thought process with be explicit about how data flows through the system and what state changes with each request, starting from API requests and ending with the response. When your request reaches your database or persistence layer, it's a great time to start documenting the relevant columns/fields of each entity. Yabat. You can do this directly next to your database visually. This helps keep it close to the relevant components and makes it easy to evolve as you iterate on your design. No need to worry too much about types here. Your interviewer can confirm and they'll slow you down. So yeah, don't waste your time documenting every column or field in your schema. You have, so what's he doing here? So for tweet, client, API gateway, CRUD service, Postgres. Tweet has ID, author ID, text, and media, S3 links array. Nice. Get, it is the same thing. You just added on this comment for tweet ID. Post. So this is for follow. V1 tweet. So we have this follow, the follower service, and the following DB Postgres. Get feed. Feed. So you get followers. Get tweets with the followers. Sounds good. This is actually smart. Astute readers probably noticed that our simple high-level design of Twitter is going to be woefully inefficient when it comes to fetching user feeds. No problem. That's exactly the sort of thing you'll need to iterate on in the deep dive section. Now that you have a high-level design in place, you're going to use the remaining 10 or so minutes to harden your design by ensuring it meets all of your non-functional requirements, addressing edge cases, identifying and addressing issues and bottlenecks, improving the design based on probes. The degree in which you're proactive in deep dives is a function of your seniority. More junior candidates can expect the interviewer to jump in here and point out places where the design can be improved. More senior candidates should be able to identify these places themselves and lead the discussion. You got to be able to lead it, even if you're a young and so for example, one of our non-functional requirements for Twitter was that our system needs to scale to 100 million daily active users. Daily active users. Okay. Is that what it said? That's probably what it said when I read it, and then I just remembered that, and now I think I'm smart. People these days. We could then lead a discussion oriented around horizontal scaling. Okay. Yeah, the introduction of caches and database sharding, updating our design as we go. I'll note there was that feeds need to be fetched with low latency. In the case of Twitter, this is actually the most interesting problem. We lead a discussion about fan out on read versus fan out on write and the use of caches. Okay. Common mistake is that they try to talk over their interviewer here. There's a lot to talk about. Senior characters, being proactive is important. However, there's balance. Make sure you give your interviewer room to ask questions and probe your design. Chances are they have signal they want to get from you, and you're going to miss it if you're too busy. Just yeah, okay, that's real. All right, core concepts. Следующий. Let me hit a casual email check. Dude, the spam mail is insane. Zero mop, dude, what is this bullshit? Frick Intel. Ничего здесь. Как, брат? Семестр уже закончил. Зачем у меня все это спам? Все это Ладно. Core concepts. Wait, let me do this. While understanding a common structure for your interview and the delivery will help you pilot it, it will not be sufficient for you to solve the problems you'll need to encounter in the interview. I'm crashing out. For this, you'll need to understand some. You'll need to understand some core concepts of system design. These are the most common. Scaling. One of the most important topics in many system design questions is how to deal with scale. While there are a lot of ways to do this, your interviewer is definitely going to want you to know how to scale a system horizontally. Horizontal scaling is all about adding more machines to a system to increase its capacity. This is in contrast to vertical scaling, which is the process of adding more resources to a single machine to increase its capacity. Bigger machines vertical, more machines horizontal. Note that more senior interviewers will recognize that vertical scaling actually requires significantly less incremental complexity. If you can estimate your workload and determine that you can scale vertically for the foreseeable future, this is often a better solution than horizontal. Many systems can scale vertically to a surprising degree. Adding machines isn't a free lunch. Oftentimes by scaling, you're forced to contend with the distribution of work, data, and state across your system. This is a common source of yellow flags in system design interviews, so let's discuss them a bit more in detail. Inexperienced candidates tend to make two mistakes. One, they leap to horizontal scaling to solve any performance problem, even when it's not necessary. Two, they don't consider the implications of horizontal scaling on the rest of the system. When you encounter a scaling bottleneck, make sure you're not throwing machines at poor design. Work distribution. The first challenge of horizontal scaling is getting the work to the right machine. This is often done via a load balancer, which will choose which node from a group to use for an incoming request. While load balancers often come with many different strategies, these connections, utilization-based, etc., simple round robin is often sufficient. For asynchronous job work, it's often done via a queue. Work distribution needs to try to keep the load on the system as even as possible. For example, if you're using a hash map to distribute work across a set of nodes, you might find that one node is getting a disproportionate amount of work because of the distribution of incoming requests. The scalability of your system is ultimately depends on how effectively you can remediate this. If one node is 90% busy and the remaining are 10% busy, you're not getting much out of your horizontal scaling. Data distribution. You also need to consider how to distribute data across the system. For some systems, this implies keeping data in memory on the node that's processing the request. More frequently, this implies keeping data in a database that's shared across all nodes. Look for ways to partition your data such that a single node can access the data it needs without needing to talk to another node. If you do need to talk to other nodes, a concept known as fan out, keep the numbers small. A common anti-pattern is to have requests which fan out to many different nodes and then the results are all gathered together. This scatter-gather pattern can be problematic because it can lead to a lot of network traffic, is insensitive to failures in each connection, and suffers from tail latency issues if the final result is dependent on every response. That's real. That's a real shite I've heard all day. If your system design problem involves geography, there's a good chance you have the option to partition by some sort of region ID. For many systems that involve physical locations, this is a great way to scale because for many problems, a given user will only be concerned with data in or around a particular location. So you can scale based on region ID. Inherently, horizontal scaling on data introduces synchronization challenges. You're either reading and writing data to a shared databases, which is a network hop away, 1 to 10 milliseconds ideally, or you're keeping multiple redundant copies across each of your servers. This means race conditions and consistency challenges. Most database systems are built to resolve some of these problems directly. Example, by using transactions. In other cases, you may need to use a distributed lock. Regardless, you'll need to be prepared to discuss how you're going to keep your data consistent. Consistency. In many system design interviews, you'll be asked to discuss the consistency of your data. Consistency at the highest level pertains to how much your users can tolerate getting stale data. A strongly consistent system will ensure that after the data is written, all subsequent reads will reflect that right. A weakly consistent, or more commonly, eventually consistent system will not make this guarantee, instead allowing for a period of time when the data is stale. Most real-life systems don't require strong consistency everywhere. For example, a social media feed can be eventually consistent. If you post a tweet, it's okay if it takes a few seconds for your followers to see it. However, a banking system needs to be strongly consistent. If you transfer money from one account to the other, it's not okay if the money disappears from one account and doesn't appear in the other. Note: many candidates will try to make a decision on consistency across their entire system. But many systems will actually blend strong and weak consistency in different parts. For example, on an e-commerce site, the system... Yeah, but yeah, sound gloopy magic. For example, on an e-commerce site, the item details might be eventually consistent. If you update the description of an item, it's okay if it takes a few minutes for the description to update on the product page. But the inventory count needs to be strongly consistent. If you sell an item, it's not okay for another customer to buy the same unit. Okay, I crashed out my paragraph. This notion of consistency applies at every layer of your design. While you might be usualing... Scheiße. Usualing? Dude, am I on crack? Okay. This notion of consistency applies at every layer of your design. While you might be using a strongly consistent database, if you insert a cache and maintain data to a time to live, the reads through that cache will eventually be consistent. Time to live. TTL database. Just like it'll be written. I think that's like it'll write it to a cache, and then after it's alive for a certain amount of time, it'll write it to the database. Yeah. Either way. Let's talk about locking. In our system, we may have shared resources which can only be accessed by one client at a time. Shared resources, one client at a time. An example might be a shared counter, like inventory units, or an interface to a physical device. Drawbridge. Okay. Locking is the process of ensuring that only one client can access a shared resource at a time. Locks happen at every scale of computer systems. There are locks in your operating system kernel, in your applications, in the database, and even distributed locks. Hence, they're a common topic in system design interviews. Locks are important for enforcing the correctness of our system, but can be disastrous for performance. In most system design interviews, you'll be forced to contend with locks when you consider race conditions. You're forced to contend with locks when you consider race. Yeah. A race condition, if you remember, is a situation where multiple clients are trying to access the same resource at the same time. This can lead to data corruption, lost updates, and other bad things. There's 3 things to worry about when employing locks. Granularity of the lock. We want locks to be as fine-grained as possible. This means we want to lock as little as possible to ensure that we're not blocking other clients from accessing the system. For example, if we're updating a user's profile, we want to lock only that user's profile and not the entire user's table. Yeah. Duration. We want locks to be held for as short a time as possible. This means that we want to lock only for the duration of the critical section. For example, if we're updating a user's profile, we want to lock only for the duration of the update and not for the entire request. Whether we can bypass the lock. In many cases, we can avoid locking by employing an optimistic concurrency control strategy, especially if the work is done either read-only or can be retried. In an optimistic strategy, we're going to assume that we can do the work without locking and then check to see if we were right. In most systems, we can use a compare and swap operation to do this. Optimistic concurrency control makes the assumption that most of the time we won't have contention in a system, which is a good assumption for many systems. That said, not all systems can use optimistic concurrency control. For example, if you're updating a user's bank account balance, you can't just assume that you can do the update without locking. Start read current record version, check version. It's the same version, process the update, write new version, and if there's a mismatch, handle the conflict. Okay. I didn't fully understand what this was, but I understand the preceding text. Oh. Indexing is about making data faster to query. In many systems, we can tolerate slow writes, but we can't tolerate slow reads. Indexing is the process of creating a data structure that makes reads faster. The most basic method of indexing is simply keeping our data in a hash map by a specific key. We need to grab the data bin that key, we can do so in O of 1 time. Suddenly, we don't need to scan the entire dataset to find the data we need. Another way of indexing is to keep our data in a sorted list. This allows us to do binary search to find the data we need in O of log n time. It's a common way of indexing in databases. There are many different types of indexes, but the principle is the same. Do a minimal amount of upfront work so that your reads can be extra fast. Indexing in databases. Most questions of indexing will happen inside your database. Depending on your database choice, you'll have different options for indexing. For example, most relational databases allow you to create indexes on any column or group of columns in a table. This isn't unbounded, however. While databases like DynamoDB allow you to create many secondary indexes, for databases like Redis, you're on your own to design and implement your own indexing strategy. If you can do indexing in your primary database, do it. Databases have been battle-honed over decades for exactly this problem, so don't reinvent the wheel unless you have to. Specialized indexes. In addition to the basic indexing strategies, there are many specialized indexes that are used to solve specific problems. For example, geospatial indexes are used to index location data. This is useful for systems that need to do things like find the nearest restaurant or the nearest gas station. Vector databases are used to index high-dimensional data. This is useful for systems that need to do things like find similar images or similar documents. Full text indexes are used to index text data. This is useful for systems that need to search for documents or search for tweets. Many mature databases like Postgres support extensions that allow you to create specialized indexes. For example, Postgres has a PostGIS extension that allows you to create geospatial indexes. If not, you'll need to maintain your indexes externally. Elasticsearch is our recommended solution for those secondary indexes when it can work. Elasticsearch supports full-text indexes searched by text via Lucene, geospatial indexes. It supports full-text indexes searched by text via Lucene, geospatial indexes, and even vector indexes. You can set up Elasticsearch to index most databases via Change Data Capture, CDC, where the ES cluster is listening to changes coming from the database and updating its indexes accordingly. Indexes or indices? Curious. This isn't a perfect solution. By using CDC, Change Data Capture, you're introducing a new point of failure and a new source of latency. The data read out of your search index is going to be stale, but that may be okay. Note: it's very common for candidates to introduce Elasticsearch as a solution to their problem without understanding its limitations or how it's used. Make sure you break up on the fundamentals so that you're ready on interview day. So yeah, this is luckily in the key technologies page. Change data capture, primary database, Elasticsearch. Communication protocols. Protocols are an important part of software engineering, but most software design interviews won't cover the full OSI model. OSI model. Where's an OSI model? Oh, okay, yeah. Bet. Okay, bet. Instead, you'll be asked to reason about the communication protocols you'll use to build your system. You've got two different categories of protocols to handle, internal and external. Internally, for a typical microservice application which constitutes 90% of system design problems, either HTTPS or gRPC will do the job. Don't make things complicated. Externally, you'll need to consider how your clients will communicate with your system. Who initiates the communication, what are the latency considerations, and how much data needs to be sent. Across choices, most systems can be built with a combination of HTTPS, SSE, security service edge. Or long polling. Oh, server-side events. Yeah, the AI is booty, bruh. Also, I feel like you should tell me what this is if I look it up and it says it's not that. Or long polling. Server-side events. And WebSockets. Browsers and apps are built to handle these protocols, and they're easy to use. And generally speaking, most service system design interviews won't deal with custom clients that need to have custom high-performance protocols. Bidirectional channel, server-side events, request response. So, use HTTPS for APIs with simple requests and responses. Because each request is stateless, you can scale your API horizontally by placing it behind a load balancer. Make sure that your services aren't assuming dependencies on the state of the client, like sessions, and you're good to go. If you need to give your client near real-time updates, you'll need a way for the client to receive updates from the server. Long polling is a great way to do this that blends the simplicity and scalability of HTTP with the real-time updates of WebSockets. With long polling, the client makes a request to the server and the server holds the request open until it has new data to send to the client. Once the data is sent, the client makes another request and repeats the process. Notably, you can use standard load balancers and firewalls with long polling. No special info needed. WebSockets are necessary if you need real-time, bidirectional communication between the client and the server. From a systems design perspective, WebSockets can be challenging because you need to maintain the connection between the client and the server. This can be a challenge for load balancers and firewalls, and it can be a challenge for your server to maintain many open connections. A common pattern in these instances is to use a message broker to handle the communication between the client and the server, and for the backend services to communicate with this message broker. This ensures you don't need to maintain long connections to every service in your backend. Lastly, server-side events are a great way to send updates from the server to the client. Okay, so these are, okay. What is long polling here? Not there. Okay, so yeah, that makes sense. They're similar to long polling, but they're more efficient for unidirectional communication from the server to the client. Server-side events allows the server to push updates to the client whenever new data is possible, without the client having to make repeated requests as in long polling. This is achieved through a single long-lived HTTP connection, making it more suitable for scenarios where the server frequently updates data that needs to be sent to the client. Unlike WebSockets, SSE server-side events is designed specifically for server-to-client communication and does not support client-to-server messaging. This makes SSE simpler to implement and integrate into existing HTTP infra, such as load balancers and firewalls. Note: statefulness is a major source of complexity for systems. Where possible, relegating your state to a message broker or a database is a great way to simplify your system. This enables your services to be stateless and horizontally scalable while still maintaining stateful communication with your clients. Yeah. Compartmentalize your state, brother. I gotta go to the bathroom. Security. When designing production systems, security should be top of mind. While system design interviews are really going to require you to do a detailed security testing of your design, they're looking for you to emphasize security where appropriate. This means that you should be prepared to discuss how you'll secure your system at the entry level. Some of the most common security concerns are authentication/auth. In many systems, you'll expose an API to external users, which needs to be locked down to only specific users. Delegating this work to either an API gateway or a dedicated service like Auth0 is a great way to make sure you're not reinventing the wheel. Your interviewer may want you to discuss the finer details like how specific entities are secured, but it's often sufficient to say, my API gateway will handle authentication and authorization. Encryption. Once you're handling sensitive data, it's important to make sure you're keeping it from snooping eyes. You'll want to cover both the data in transit via protocol encryption and the data at rest via storage encryption. HTTPS is the SSL/TLS protocol that encrypts data in transit and is the standard for web traffic. If you're using gRPC, it supports SSL/TLS out of the box. For data at rest, you'll want to use a database that supports encryption or the data yourself. For the data at rest, you'll want to use a database that supports encryption or encrypt the data yourself before storing it. Note, for sensitive data, it can often be useful for the end user to control the keys. This is a common pattern in systems that need to store sensitive data. For example, if you're building a system that stores user data, you might want to encrypt that data with a key that's unique to each user. This way, even if your data is compromised, the data is still secure. Okay. Data protection. Data protection is the process of ensuring that data is protected from unauthorized access, use, or disclosure. Frequently, production systems are concerned with data that's sensitive when exposed, but might not be within a certain authorization path. Production systems are concerned with data that's sensitive when exposed, but might not be within a authorization path. A user's data might be exposed via a create friend request. Many exposures of this sort are discovered by scraping endpoints, so having some sort of rate limiting or request throttling is a good idea. Okay. Data protection is the process of ensuring that monitoring. Once you've designed your system, some interviewers will ask you to discuss how you monitor it. Their idea here is simple. Candidates who understand monitoring are more likely to have experience with actual systems in production. Monitoring real systems is also a great way to learn about how real systems scale and break. Monitoring generally occurs at 3 levels, so it's useful to name them. Infrastructure monitoring. Infrastructure monitoring is the process of monitoring the health and performance of your infrastructure. This includes things like CPU usage, memory usage, disk usage, and network usage. This is often done using a tool like Datadog or New Relic. While a disk usage alarm, shout out New Relic by the way, frick Datadog. While a disk usage alarm may not break down your service, it's usually a leading indicator of problems that need to be addressed. Service level monitoring. Service level monitoring is the process of monitoring the health and performance of your services. This includes things like request latency, error rates, and throughput. If your service is taking too long to respond to requests, it's likely that your users are having a bad time. If throughput is spiking, it may be that you're handling more traffic or your system may be misbehaving. Application level monitoring. Application level monitoring is the process of monitoring the health and performance of your application. This includes things like the number of users, the number of active sessions, and the number of active connections. This could also include key business metrics for the business. This is often done with a tool like Google Analytics or Mixpanel. This is often the most important level of monitoring for production for product design interviews. Okay, I might buy this. Key technologies. System design involves assembling the most effective building blocks to solve any problem. To solve a problem. Therefore, it is crucial to have a good understanding of the most commonly used building blocks. Involves assembling the most effective building blocks to solve a problem. Okay. Therefore, it is crucial to have a good understanding of the most commonly used building blocks. Agreed. Most interviewers aren't going to care whether you know about a particular queuing solution, so long as you have one you can use. However, if you don't know about any queuing solutions, you're going to have a hard time designing a system that requires one. In this section, we'll outline the key technologies relevant to solving 95% of system design problems, together with some discussion of the possible options for each. Keep in mind from the leveling section that the amount of depth your interviewer is likely to probe is proportional to the level that you're interviewing at. A mid-level candidate who can roughly describe Elasticsearch as a search index is likely to be fine, but a senior candidate who can't describe the inverted index or the reason about its scaling is likely to be a yellow flag. In either case, focus on breadth before depth. Core database. Almost all system design problems will require you to store some data, and you're most likely going to be storing it in a database or in blob storage. While there are many different types of databases, the most common are relational databases like Postgres and NoSQL databases like DynamoDB. We recommend you pick one of these for your interview. Really? We recommend you pick one of these for your interview. If you are taking predominantly product design interviews, we recommend you pick a relational database. If you are taking predominantly infrastructure design, we recommend you pick a NoSQL database. I don't understand that. Many candidates trip themselves up over Many candidates trip themselves up by trying to insert a comparison of relational and NoSQL databases into their answer. The reality is that these two technologies are highly overlapping, and broad statements like, I need to use a relational database because I have relationships in my data, or I've got to use NoSQL because I need scale and performance, are often yellow flags that reveal inexperience. The truth is that most interviewers don't need an explicit comparison of SQL and NoSQL databases in your session, and it's a pothole you should completely avoid. Instead, talk about what you know about the database you're using and how it will help you solve the problem at hand. If you're asked to compare, focus on the differences in the databases you're familiar with and how they will impact your design. So, I'm using Postgres here because its ACID properties will allow me to maintain data integrity as a great leader. Relational databases. What is a relational database and when should you use it? Relational databases, sometimes called relational database management systems, are the most common type of database. They're often used for transactional data, e.g., what is e.g.?
Sample of academic writing, e.g., a dissertation chapter. Because they're Welcome to Ask the Editor. I'm Peter Sokolowski, editor-at-large at Merriam-Webster. The most looked up abbreviations in our online dictionary are IE and EG, probably for the simple reason that they are so often confused for one another. Both of these are abbreviations of Latin expressions. IE stands for id est, which means that is in Latin. It introduces a rewording or a clarification of a statement that has just been made, or of a word that has just been used, such as the cough may last for a short period of time, i.e. 3 to 5 days. EG stands for exempli gratia in Latin, which means for example. It introduces one or more examples that illustrate something stated, such as submit a sample of academic writing, e.g. a dissertation chapter. Because their usage can seem similar, these abbreviations are often confused. Just remember that IE and that is both share an I, and that example and EG both share an E. You can also try substituting the English for the abbreviation. The cough may last for a short period of time, that is, 3 to 5 days. Submit a sample of academic writing, for example, a dissertation chapter. Even though English is a Germanic language, we owe a huge debt to Latin. You don't need to be an MD or have any PhD on your CV to see that English has borrowed pounds of words from Latin. We use Latin day and night, AM and PM, and without it, we'd have to say RIP to huge swaths of English. P.S. Latin isn't the only language to have an impact on English. There's French, Spanish, Arabic, Greek, etc. But Latin is foundational, QED. Post scripta, ut plus cinematographicas videres, visita nostrum locum in tela, merriam-webster.com. Welcome to Ask the
It kind of cooked at the end, can't lie to you.
Welcome to Ask the Editor. I'm Peter Sokolowski, editor-at-large at Merriam-Webster. To huge swaths of English. P.S. Latin isn't the only language to have an impact on English. There's French, Spanish, Arabic, Greek, etc. But Latin is foundational, QED. Post scripta, ut plus cinematographicas videres, visita nostrum locum in tela, merriam-webster.com.
So to become a crack dev, you need Tmux, Vim, Arch Linux, InfluxDB. You need a split keyboard, crappy headphones, crappy mouse, Bash, Python, gRPC, and CPP. You need CMake. You need an eyeball. What is that? I'm not sure if I've seen that. I kind of recall that a bit. You need light mode. You need Tmux. I think I said that. Split keyboard. Agreed. That's about it. Probably Bash. Probably CPP. Yeah, everything else is optional. All right. e.g. user records, order records. They're often used for transactional data, like order records, user records, etc. e.g. and etc. in the same sentence, the same parenthesis. No period though. Yeah, but. And are typically the default choice for a product design interview. Excuse me. Relational databases store your data in tables, which are composed of roles and I'm coaching. Many call it. Brad. Zacham. All right. Relational databases store your data in tables, which are composed of rows and columns. Each row represents a single record, and each column represents a single field in that record. For example, a users table might have a name column and an email column. Relational databases are often queried using SQL, a declarative language for querying data. Learning how our relational database management systems work under the covers, is beyond the scope of this guide, but we recommend you to read a deep dive into how databases work if you're interested in reading more. Understanding how data flows internally through a database is a microcosm of the tricks you can use in your system design interview to optimize for performance and scale. Ooh, that's kind of dope. Just building a database in C. It's actually not unreasonably long. Kind of cool. But I ain't doing all that right now, at least. For example, a users table might have a name column and an email column. Sounds good. Relational databases are often queried. Yeah, I already read that, bro. Yeah. Things you should know about relational databases. Beyond simply storing data, relational databases come equipped with several features which are useful for system design interviews. The most important of these are SQL joins. Joins are a way of combining data from multiple tables. For example, if you have a users table and a post table, you might want to query all posts for a particular user. This is important for querying data, and SQL databases can support arbitrary joins between tables. Indexes. Indexes are a great way of storing data in a way that makes it faster to query. For example, if you have a users table with a name column, you might create an index on the name column. This would allow you to query for users by name much faster than if you didn't have an index. Indexes are often implemented using a B tree or a hash table. The great thing about relational databases is their support for arbitrarily many indexes, which allows you to optimize for different queries and their support for multi-column and specialized indexes, like geospatial indexes or full-text indexes. RDBMS transactions. Transactions are a way of grouping multiple operations together into a single atomic operation. For example, if you have a users table and a post table, you might want to create a new user and a new post for that user at the same time. If you do this in a transaction, either both operations will succeed or both will fail. This is important for maintaining data integrity. What are the most common relational databases? Postgres and MySQL. You can pick either of them. Recommend Postgres. NoSQL databases. What is a NoSQL database and should you use it? NoSQL databases are a broad category of databases designed to accommodate a wide range of data models, including key value, document, column family, and graph formats. Unlike relational databases, NoSQL databases do not use a traditional table-based structure and are often schemaless. Flexibility allows NoSQL databases to handle large volumes of unstructured, semi-structured, or structured data and to scale horizontally with ease. NoSQL databases are strong candidates for situations where flexible data models, your data model is evolving or you need to store efficient data model is evolving or you need to store different types of data without a fixed schema. Scalability. Your application needs to scale horizontally to accommodate large amounts of data or when high. Your application needs to scale horizontally to accommodate large amounts of data or high user loads. Handling big data and real-time web apps. You have applications dealing with large volumes of data, especially unstructured data, or applications requiring real-time data processing and analytics. The places where NoSQL databases excel are not necessarily the places where relational databases fail and vice versa. For example, while NoSQL databases are great for handling unstructured data, relational databases can also have JSON columns with flexible schemas. While NoSQL databases are great for scaling horizontally, relational databases can also scale horizontally with the right architecture. When you're discussing NoSQL databases in your system design interview, make sure you're not making broad statements, but instead discussing the specific features of the database you're using and how they will help you solve the problem at hand. Things you should know about NoSQL databases. Data models. NoSQL databases come in many different flavors, each with its own data model. The most common types are key value stores, document stores, column family stores, and graph databases. Consistency models. NoSQL databases offer various consistency models ranging from strong to eventual. Strong consistency ensures that all nodes in the system have the same data at the same time, while eventual consistency ensures that all nodes will eventually have the same data. Indexing. Just like with relational databases, NoSQL databases support indexing to make data faster to query. Most common types are B-tree and hash table indexes. NoSQL databases scale horizontally using consistent hashing and/or sharding. Most common NoSQL databases are DynamoDB and MongoDB. Both of these databases have its own strengths and weaknesses. Yeah, I don't know how to do the grammar there. But for the purposes of a system design interview, you can pick either of them and be fine. If you don't already have a favorite, pick Dynamo. Blob storage. Sometimes you'll need to store large, unstructured blobs of data. It could be images, videos, or other files. Storing these large blobs in a traditional database is both expensive and inefficient and should be avoided when possible. Instead, you should use a blob storage device like Amazon S3 or Google Cloud Storage. These platforms are specifically designed for handling large blobs of data and are much more cost-effective than a traditional database. Blob storage devices are simple. Blob storage services are simple. You can upload a blob of data and that data is stored in a get back URL and get back a URL. You can then use this URL to download the blob of data. Oftentimes, blob storage devices work in conjunction with CDNs, so you can get fast downloads from anywhere in the world. Upload a file/blob to blob storage, which will act as your origin. Then use a CDN to cache the file blob in edge locations around the world. Warning. Avoid using blob storage like S3 as your primary data store unless you have a very good reason. In a typical setup, you will have a core database like Postgres or DynamoDB that has pointers to the blob stored in S3. This allows you to use the database to query and index the data while still getting the benefits of cheap blob storage. Here are some common examples of when to use blob storage. Design YouTube. Store videos in blob storage, metadata in a database. Instagram. Images and videos in blob storage, metadata in a database. Store files in Dropbox. Store files in blob storage, store metadata in a database. So, client, server. Send big things to blob storage, the core database. has metadata. S3 image URL points to the image resource in S3. Blob storage points to CEN. So you have multiple of these, and they cache the blob storage. They send it to the client. Cool. Durability. Blob storage services are designed to be incredibly durable. They use techniques like replication and They use techniques like replication and erasure coding to ensure that your data is safe even if a disk or server fails. Cool. Scalability. Hosted blob storage solutions like AWS S3 can be considered infinitely scalable. They can store an unlimited amount of data and can handle an unlimited amount of they can store an unlimited amount of data and can handle an unlimited amount of requests within the limits of your account. As a result, in your interview, you don't need to explicitly consider the scalability of blob storage devices. Consider this as a given. Blob storage services are designed to be cost effective. They're much cheaper for storing large blobs of data than in a traditional database. For example, AWS S3 charges 2 cents per gigabyte per month for the first 50 terabytes. This is much cheaper than doing it in DynamoDB, which is $1.25 per gigabyte per month. Blob storage services have built-in security features like encryption at rest and in transit. They also have control features that allow you to control who can access your data. Upload and download directly from the client. Blob storage services allow you to upload and download blobs directly from the client. This is useful for applications that need to store and retrieve large blobs of data like images or videos. Familiarize yourself with pre-signed URLs and how they can be used to grant temporary access to a blob. Blob pre-signed URLs. Chunking. When uploading large files, it's common to use chunking to upload the file in smaller pieces. This allows you to resume and upload if it fails partway through, and it also allows you to upload the file in parallel. That's kind of good. This is especially useful for large files, where uploading the entire file at once might take a large time. Modern blob storage services like S3 support chunking out of the box via the multi-part upload API. That's kind of dope. Examples of blob storage services. Amazon S3 Cloud, Google Cloud. Search optimized database and when should you use it. Sometimes you're tasked with implementing full text search. Full text search is the ability to search through a large amount of text data and find relevant results. It's different from a traditional database query, which is usually based on exact matches or ranges. Without a search optimized database, you would need to run a query that looks something like this. Select star from documents where document text like search term. This query is slow and inefficient, and it doesn't scale well because it requires a full table scan. Search optimized databases, on the other hand, are specifically designed to handle full text search. They use techniques like indexing, tokenization, and stemming to make search queries fast and efficient. In short, they worked by building what are called inverted indexes. Inverted indexes are a data structure that maps from words to the documents that contain them. This allows you to quickly find documents that contain a given word. A simple example of an inverted index might look like this. Word 1 is in doc 1, 2, 3, 2, 3, 4, 1, 3, 4. Examples here are straightforward. Consider an application like Ticketmaster that needs to search through a large number of events to find relevant results. Or a social media platform like Twitter that needs to search through a large number of tweets to find relevant results. In either case, a search-optimized database would be an optimal choice. Things you need to know about search-optimized databases. Inverted indexes. As just mentioned, search-optimized databases use inverted indexes to make such queries fast and efficient. An inverted index is a data structure that maps from words to the documents that contain them. This allows you to quickly find documents that contain a given word. Tokenization. Tokenization is the process of breaking a piece of text into individual words. So it allows you to map from words to documents in the inverted index. Stemming. Stemming is the process, so let's also look up. I'm going to need more on search optimized databases. Or just read this deep dive on Elasticsearch. Boom. Fuzzy search. Fuzzy search is the ability to find results that are similar to a given search term. Most search optimized databases support fuzzy search out of the box as a configuration option. In short, this works by using algorithms that can tolerate slight misspellings or variations in the search term. This is achieved through techniques like edit distance calculation, which measures how many letters need to be changed, added, or removed to transform one word into another. Scaling. Just like traditional databases, search optimized databases scale by adding more nodes to a cluster and sharding data across these nodes. Query Leader is Elasticsearch. Distributed RESTful search and analytics engine built on top of Apache Lucene. It is designed to be fast, scalable, and easy to use. It is the most popular search optimized database and is used by companies like Netflix, Uber, and Yelp. API Gateway. Dude, this is actually a lot of content. This is actually like a crazy amount of content. Let me adjust my calendar right quick, because I am actually enjoying this. But I have been doing this for a few hours. So I'm going to do probably around an hour and 15 more of this. Could be more, though. So I got to finish the Gleam Depths issue. Got 4 hours and 30 minutes for that. Make a buffer to eat lunch. I'll give myself 5 hours for the Gleam Depths issue. Another 2 hours for system design. Damn, this system design in a hurry is actually really clutch because it's saving me a ton of time. So I'm going to push DDIA to the back. Extend this an hour. Do some K8's book here. Should probably just start with, do like an hour of lead. 3 hours order book, eat. Just do some lead. All right, doing good. Doing good so far. So if I finish this, also like my neck is starting to hurt. kind of been doing pretty good the last few weeks. Let's keep it up. So API gateway. So how much have I read right now? So now I'm at API gateway. Okay, I haven't actually read that much. API gateway. I'm gonna just stop talking now. Get some water. Just like a stick. I'm actually gonna wash this blanket as well. Just so I can move it around. I'm gonna put on a YouTube, probably leetcode, and eat my lunch.
Hey everyone, welcome back, and let's write some more leetcode today. So today let's
Same
solve
thing, right? It's
find
like 10
median
mils.
from a data stream.
Wouldn't have
So
it
this
any
is
other way.
another hard problem, but it's not
And see something that's actually on programming and not clickbait. Dude, does this guy even make? What's this?
Hey everyone, welcome
Sure.
back, and let's write some more leetcode today. So today let's solve the problem maximum performance of a team. Before we get started, I just want to quickly mention, if you haven't heard, I recently launched LeetCode Pro. There's a 25% off launch sale going on right now. If you're preparing for coding interviews, I highly recommend checking it out. You can get lifetime access to all current and future courses. For now, I'm focusing on coding interview prep, but in the future, I want to expand to a lot of other things like full stack web development, cybersecurity, maybe even machine learning. If you like my teaching style, I think the courses are going to be really helpful for you. Okay, but back to the problem at hand, and I'm not gonna lie, this one's actually pretty tricky dicky. We're given two integers n and k. We're also given two integer arrays, which represent the speed and efficiency of a bunch of engineers. We're actually given n engineers, and n is going to be the length of each of these arrays. So the speed of the ith engineer is going to be speed at index I, and the efficiency of the ith engineer is going to be the efficiency at index I. Now we can choose at most k engineers out of the n engineers to form a team. And what we want to do is try to maximize the performance. The performance is measured as the sum of the engineers' speeds multiplied by the minimum efficiency among all of those engineers. So this is pretty abstract and complicated. Also, the number could be really big, so we actually want to return the result modded by this value. So at first you might think this is a dynamic programming problem. It's kind of reminiscent of the 0-1 knapsack problem, because each of these engineers, we can choose to include them or not include them, and we can choose at most k engineers. But the calculation in this case can make things pretty complicated. There's actually an easier and more efficient way to solve this problem, which I'll explain, but first let's walk through the intuition. So these are our arrays. E is for efficiency, S is for speed. So this is an engineer, this is an engineer, etc, etc. Now the most brute force way to solve this problem, for every position here, we choose, do we want to include this engineer or not? So one possibility would be to include the engineer. They have an efficiency of 5, a speed of 2, and one would be to not include them at all. And then we could keep making a decision tree like this, where each path of the decision tree should have at most k engineers. And then among all of the paths, we would calculate the efficiency, which we would get by taking the sum of all the speed values for that path and take the minimum of the efficiency values of that path and then multiply those two together. And then among all those values, we would want to get the maximum of those. Now, obviously, this is not going to be super efficient. The time complexity is going to be 2 to the power of n. That's going to be the size of this decision tree. But there's a better way to do it. And it has to do with how we can go ahead and think about this problem. Remember, we can choose at most k engineers. We don't have to choose exactly k engineers. And remember, when we calculate the efficiency, we're going to take the minimum efficiency among all of the engineers. So let's think about this problem in a different way, and I bet it's going to make things a lot more simple for you. Let's first try to maximize the efficiency. Among all of these efficiency values, which one is the maximum? It's 9. So I want to calculate what's the maximum performance we could possibly get with an efficiency of 9. Well, the answer is actually very, very simple. So this engineer with an efficiency of 9 has a speed of 1. So the calculation with just this one engineer would be the minimum of efficiency. So in this case, the minimum would be the single efficiency we have, which is 9. The sum of all the speeds is just going to be 1. So we add those two together, we get 9. That's the performance here. Can we get a performance any higher than this if we have a minimum efficiency of 9? The answer is no, because if we add any more engineers to our current set, if we add this guy, we've lowered the efficiency. If we add this guy, we lowered the efficiency. So the maximum performance we can get when we have an efficiency of 9 is just this. This is the solution. So we were trying to be greedy, and that's the value that we calculated. Now let's try what's the maximum performance we can get when we have an efficiency of the second smallest value. It's possible that with an efficiency of 7, we can get a higher performance. So when we have an efficiency of 7, we have just this engineer who has a speed of 5. We can't include any of the other engineers that have a smaller efficiency than 7, because at this point, what we're trying to do is calculate the max performance with an efficiency of 7. We're basically going through every efficiency value in descending order from largest to smallest, calculating what's the maximum performance we could get. In this case, the only other engineer we can include is the one that had an efficiency of 9. So here we have 2 engineers, and that's okay because our K value in this case, in this example, is equal to 2. So we're allowed to have these 2 engineers. So what's the maximum performance we could get with these 2 guys? Well, the efficiency is going to be the minimum of these 2. Straightforward, it's just 7. That's what we were expecting anyway. And then multiplied by adding their speeds together, 1 plus 5 is equal to, so this is 6 times 7, that's 42. So this is larger than the previous value we had, which was 9. So this is a higher performance. Let's continue the algorithm. By the way, what we realized is since we're going through these efficiencies in descending order, we should actually take this array and sort it in descending order with efficiency and sort the speeds corresponding, because we know each efficiency is tied to a speed, so we want the relative order of these to be preserved. So now engineers. So that have a smaller efficiency than 7, because at this point what we're trying to do is calculate the max performance with an efficiency of 7. We're basically going through every efficiency value in descending order from largest to smallest, calculating what's the maximum performance we could get. In this case, the only other engineer we can include is the one that had an efficiency of 9. So here we have 2 engineers, and that's okay because our k value in this case, in this example, is equal to 2. So we're allowed to have these 2 engineers. So what's the maximum performance we could get with these 2 guys? Well, the efficiency is going to be the minimum of these 2. Straightforward, it's just 7. That's what we were expecting anyway. And then multiplied by adding their speeds together, 1 plus 5 is equal to, so this is 6 times 7, that's 42. So this is larger than the previous value we had, which was 9. So this is a higher performance. Let's continue the algorithm. By the way, what we realized is since we're going through these efficiencies in descending order, we should actually take this array and sort it in descending order with efficiency and sort the speeds corresponding, because we know each efficiency is tied to a speed, so we want the relative order of these to be preserved. So now we're going to continue our algorithm. We already calculated what the max performance would be if we had an efficiency of 9. We also did the same for 7. Now let's do the same for these 4. But before we do, I want to quickly mention when we were at this point, our only choice was to include an engineer that came to the left of it, which was this guy. And we're allowed to choose at most 2 engineers because that's what our k value is. Is there any reason why we would not want to include a previous engineer? Because in this case, we're guaranteed that all the speed values are going to be positive, all the efficiency values are going to be positive. We know that the previous engineer's efficiency won't matter at all because this guy has a smaller efficiency, so this is the value that would be used anyway. But we know that the engineer does have a speed, it would be a positive value, so there's never going to be any downside to including an extra engineer if we have the choice to do so. When we were calculating with an efficiency of 9, we did not have a choice to include any other engineers. So now, when we get to the next efficiency, 5, we have this engineer who has a speed of 2. Our k value is 2, so we can only choose one of these previous engineers. Like I just said, their efficiency makes no difference to us. We have to choose the smallest efficiency anyway, but their speeds matter. We want to choose the engineer with a higher speed. It turned out to be this guy, so we would get the 5. Now, the naive way to do this would be with nested for loops. We would just iterate through every previous engineer and get the one with the maximum speed. But there's a better way to do that. We can actually have a heap, a minimum heap of all the previous engineers that we visited, and the value we add to the heap is not going to be their efficiency, of course, it's going to be their speed. So why am I using a minimum heap though? I thought we wanted the maximum speed. Well, we're going to pop the minimum. We're going to pop this guy. We're going to keep track of the engineers with the highest speed in the heap. So then when we do our calculation, we're going to remove this guy and we're going to see that there's a 5 already in the heap, and we're actually going to have a running total of what our speed is so far. So originally the speed was 1 from this guy, and then we added a 5 to it, so it was then 6. Then we added a 2 here, so then it became 8, but then we had too many engineers. We had to remove one, so we removed this guy, so we subtracted 1, and then we were left with a 7. So that's our speed at this point. And what's the efficiency? Well, that's the easiest part. It's 5 here because this is the minimum one. So we have 5 times 7, which is the total speed. So that's 35. So that's not the largest, or previously we saw a 42. So this is not the largest so far. But let's go now to the next efficiency, which is 4. Again, we're going to pop the one that had the minimum speed. So among these two, we're going to pop this guy. So now to calculate the performance, we get 4, which is the efficiency, times 5 plus 10, which is 15. We add those two together, that's 60. And actually, that's going to be the result for this example. Where we can continue this example, I'll do so very quickly to show you how it runs, but then we're going to jump into the code. By the way, what's the time complexity of what we're talking about? Well, we had to sort the input array, so that's n log n. Also, we're iterating through this array, which is n. We're pushing and popping from our min heap, but our heap is only going to be of size k, so that's going to be time complexity n times log k. So the overall time complexity is going to be these two added together. This one is larger, so that's the overall time complexity because we have to sort the input array. So running through the rest of this code, now we're going to be calculating with an efficiency of 3. This is the smallest efficiency we have so far. Among these two, we're going to pop the one with the lowest speed. So we're going to pop this guy. So now we're left with these two. We're going to calculate the performance. It's going to be 3 times 10 plus 3. That's 13. So this is 39. That's obviously not the solution. None of these are going to be the solution. Then we would go to the next efficiency. Among these two now, we're going to pop the one with the smallest speed. It was this guy. So pop him. Now, with an efficiency of 2, we're going to multiply that by the total speed among these two guys. 10 plus 8 is 18. That's 36. That's, again, not the solution. So the max we found was 60. That's what we would have returned. Now let's code it up. So moving on to the code, the first thing we want to do, remember, is basically combine the two arrays into a single array of pairs because we want to sort by efficiency in descending order, but we also want each efficiency to have a corresponding speed. So what we're going to do in Python, it's pretty cool. You can actually iterate through two arrays at the same time. So we're going to zip these two arrays together. Efficiency is going to come first and speed is going to come second. This allows us to iterate through both of them at the same time. So efficiency is going to give us a value from the efficiency array. Speed is going to give us a value from the speed array. We're building up our eng array. So we're going to append to this guy a pair. The first value is going to be the efficiency. The second value is going to be the speed of that engineer. After we've built it, we do want to sort it in descending order. In Python, you can do that pretty easily by setting reverse equal to true. Now we're going to get to the fun part. We're going to have two variables which are going to keep track of our result, which is the max performance we've seen so far, and a second variable which is going to give us our total speed so far among all the engineers in our min heap. Because remember, the engineers in our min heap are the ones we're considering. Both of these are initially going to be set to 0. We're going to create our min heap, which is initially going to be empty. Then we're just going to simply iterate through every single engineer in our array of engineers. We're going to get their efficiency and their speed. Now, typically what we're going to want to do is to the total speed, we want to add the speed of this current engineer. And we also want to take this engineer and add them to the min heap. So in Python, you can do that like heapq.heap push to the min heap this value, which is their speed, because that's what we care about. And to calculate the result, so the current result so far, given this efficiency, remember, we're using this efficiency. So we want to maximize the result. We're going to set the result equal to the max of itself and the performance that we're calculating right now, which is going to be the efficiency multiplied by the total speed so far. So this is pretty much the entire solution. The only thing we didn't cover is what happens when our heap grows too large. We're pushing to this heap, but what if it already had k elements added to it? Well, before we do anything then, what we want to check is if the length of our min heap is exactly equal to k, then we have to pop from the min heap. So we're going to say heapq.heap pop from that min heap, which is going to pop the speed value. Remember, if we remove an engineer, then we can't consider their speed as a part of the total speed. So what we have to say is from the total speed, we're going to subtract the value that we just popped right now. So that will make sure that we have at most k engineers at a time. So this loop will calculate the max performance given every possible efficiency, and then the maximum will be contained in the result, so we can return that. Don't forget, though, that we have to mod it by 10 to the power of 9 plus 7. So let's run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. If this was helpful, please like and subscribe. If you enjoy my teaching style, consider checking out leetcode.io. It has a bunch of free resources to help you prepare for coding interviews. You can also get lifetime access to every if you enjoy my teaching, sure that it works. And
put this plate up and then we'll talk about this problem.
consider their
Yeah, I understand this intuition. I'm just curious the PQ implementation, really. Six engineers with this speed and efficiency. Speed of 2, efficiency 5. Shout out efficiency 5. So is he sorting it? I'm so curious how you do the zip. How do you C++ zip? Okay, so let's do this. Int modulo equal to casting of int math.pow 7. Understood. So he's making a list of a pair of integer to integer. Oh, that's Java. What the? Oh, yucky. So he's got a vector, got a pair of int uh, imps. Sorry, is that So build it. For int I equals 0, I is less than n, I plus plus. Going to do imps of I is equal to. So we're constructing a pair here. Efficiency of I, speed of I. So sort based on the candidates, or sort the candidates. Sort imps dot begin, imps dot end. Okay. Long speed local speed sum equals 0 and it's 0. Priority queue int, so it's a min heap. Int vector int creator int pq for so each pair, so for auto es int imps. So push it to the priority queue. Add the speed. Local speed sum this equals s. The other priority queue. For each pair. Put the speed to the priority queue. Local speed sum. If pq.size is greater than k. Oh, so this is a bit different. So this is not actually local. This is a bit smarter, actually. Speed sum minus equals pq.top. pq.pop. Ants equals max of ants. Speed sum times the efficiency. It's percent. See, I don't actually understand why you want to do that there. Why don't you just do it here? Reverse order. 67. Интересно. It's looping from the back. If I plus 1 is less than n, this performance is equal to max of performance plus the current speed plus the items of I dot second times the items of I dot first. EQ to push. For each pair, push it. Push it to the heap. It's going to be a min heap. So you add the sum, you add the speed sum, minus equals. Wait, so you push the speed to the priority queue. Add the speed to the sum. Then, if the size, so imps is sorted, so we're at the biggest one. Push the speed. If the size is greater than k, then you remove the one with the least amount of speed. You set the answer to the maximum of the answer and the speed sum times a. So this will end. So E is, you multiply the lowest efficiency. So we're going from high efficiency to low efficiency. Going from high efficiency to low efficiency. Maintaining your priority queue of the speeds. So you just keep adding them. You increment the sum of all the speeds in there. If you're exceeding size, you want to evict, or you want to remove. That's kind of evicting. You want to remove the worst one. You want to remove the one that's, because if the efficiency is larger, it's free. And why are we removing the one with the lowest speed? Can begin turn. Cannot begin turn. I actually fall asleep. If I could just snoozing, man. Hit like a minute snooze. Can begin turn. Cannot begin turn. I actually fall asleep. Dang, bro. Shut up. All right. Let's rewrite this from scratch after falling asleep. So we're gonna need a vector events, yeah. Or we want a vector of pairs of ints. We can call this imps size a. So this vector is gonna be sorted employees. High to low based on efficiency. So how do we do that? We get an int I equals 0, I is less than n, I plus plus. Then we just do imp.push back. pair with speed of efficiency of speed of and you sort it, so you go sort in the reverse order, so sort imps or begin imps rend. So now we have that. So we're gonna need a sum, about a speed sum, initialize 0. We're gonna need an ants, initialize 0. We're also gonna need a priority queue of int. This is a priority queue of speeds. I think it's just priority queue of int. 4. So we can just have an auto reference to this pair and imps. What do we do? So you start off PQ, you add. So it's not EQ, it's ES. You add the speed. And then since you add the speed in there, you got increment speed sum. Speed sum plus equals S. Now, if you're exceeding the capacity, so this is when PQ.size is greater than K. If you're doing this, you want to evict the worst one. So you're going to do PQ or speed sum minus equals PQ.top. PQ.pop. And then sounds right to me. Return ants modulo IE 9 plus 7. So it has to be IE 9 plus 7. Only a double, so we're gonna have to cast this to a error int. So yeah, we gotta do ants. Whatever changing ants. Ants is equal to the max of ants. And speed sum times E, yeah. Or bit off. When K equals 2, we're getting 42. Vector, we push back. I'm sorry, begin, alright. So. Push it on the priority queue. This is sorted greatest. It needs to be sorted. This needs to be a min heap. So you do that. Great. Let's go back to reading this. What is an API gateway and when should you use it? So an API gateway handles auth, rate limiting, and logging, and it routes to the next service. Remember when Gateway used to make laptops? They still make laptops? $160 for a laptop. That's actually not horrible. That's actually not that bad. I'm kind of impressed with that. But let's keep. What is a load balancer? Most system design problems will require you to design a system that can handle a large amount of traffic. So does this not handle load balancing? This handles rate limiting. When you have a large amount of traffic, you will need to distribute that traffic across multiple machines to avoid overloading any single machine for horizontal scaling. And also did I, yeah. Let me just reset up my drawing setup here. All this. Ладно. I'm curious how much this costs. Meta, sure. 170. Intern. Oh, hell. Senior staff engineer is crazy. Ебачик. I know that's cursed. Я это увидел, я не думал, что это было так круто. Об этом я не знаю. Это вообще не работает. Ну, молодец, молодцы. Русский поговорение. $20. Учим английский. Ладно. Это мальчик сам. Блин. Ебашик. You get it? Because I mean, alright, I gotta do the bathroom. This is where load balancer comes in. You can assume that your load balancer is a black box that will distribute work across your system. The reality is that you need a load balancer wherever you have multiple machines capable of handling the same request. However, in an interview, it can be redundant to draw a load balancer in front of every service. Instead, just either omit a load balancer from your design altogether and just mention that these services are horizontally scaled, or add only one to the front of the design as an extraction. Most common load balancers, Elastic. Nginx as a load balancer? That kind of makes sense. Wait, F5 engine. Who maintains Nginx? Ah. I did not know that. That makes sense. Queues. Queues serve as buffers for bursty traffic or as a means of distributing work across a system. A compute resource sends messages to a queue and forgets about them. On the other end, a pool of workers processes the messages at their own pace. Messages can be anything from a simple string to a complex object. Warning, be careful of introducing queues into synchronous workloads. If you have strong latency requirements like under 500 milliseconds, a queue is going to break that. Use them as a buffer for bursty traffic. In a ride-sharing app like Uber, queues can be used to manage sudden surges in ride requests. During peak hours or special events, ride requests can spike massively. A queue buffers these incoming requests, allowing the system to process them at a manageable rate without overloading the server or degrading the user experience. Distribute work across the system. In a cloud-based photo processing service, queues can be used to distribute expensive image processing tasks. When a user uploads photos for editing or filtering, these tasks are placed in a queue. Different worker nodes then pull tasks from the queue, ensuring even distribution of workload and efficient use of computing resources. Excuse me. So your producers. It's a little too big. Okay. Producers send messages in the queue. They store messages, dispatch them to consumers, acknowledge receipt, and remove the message in the queue. Okay. Things you should know about queues for your interview. Most queues are first in, first out. Kafka is a queue which allows for more complex ordering, such as priority or time. Retry mechanisms. Many queues have built-in retry mechanisms that attempt to redeliver a message a certain number of times before considering it a failure. Failure to the consumer. Okay. You can configure retries, including the delay between attempts and the maximum number of attempts. Dead letter queues. They're used to store messages that cannot be processed. They're useful for debugging and auditing, as it allows you to inspect messages that fail to be processed and understand why. Scaling with partitions. Queues can be partitioned across multiple servers so they can scale to handle more messages. Each partition can be processed by a different set of workers, just like databases. You will need to specify a partition key to ensure the related messages are stored in the same partition. Back pressure. Back pressure is a way of slowing down the production of messages when the queue is overwhelmed. This helps prevent the queue from becoming a bottleneck in your system. For example, if a queue is full, you might want to reject new messages or slow down the rate at which new messages are accepted, potentially returning an error to the user or producer. Streams and event sourcing. What are streams and when should you use them? Sometimes you'll be asked a question that requires either processing vast amounts of data in real time or supporting complex processing scenarios, such as event sourcing. Event sourcing is a technique where changes in application state are stored as a sequence of events. These events can be replayed to reconstruct the application state at any point in time, making it an effective strategy for systems that require a detailed audit trail or the ability to reverse or replay transactions. In either case, you'll likely want to use Друзья есть. In either of these cases, you'll likely want to use a stream. Unlike message queues, streams can retain data for a configurable period of time. Allowing consumers to read and reread messages from the same position or from a specified time in the past. Streams are a good choice when you need to process large amounts of data in real time. Imagine designing a system for a social media platform where you need to display real-time analytics of user engagements on posts. Excuse me. You can use a stream to ingest high volumes of engagement events generated by users across the globe. Stream processing Sigmum. Dude, I'm fucked. A stream processing system like Apache Flink or Spark Streaming can process these events. Oh my god. Can process these events in real time to update the analytics dashboard. When you need to support complex processing scenarios like event sourcing. So consider a banking system where every transaction, deposits, withdrawals, transfers, needs to be recorded and could affect multiple accounts. Using event sourcing with a stream like Kafka, each transaction is an event that can be stored, processed, and replayed. This setup not only allows for real-time processing of transactions, but also enables the bank to audit transactions. Setup not only allows for real-time processing of transactions, but also enables the bank to audit transactions, rollback changes, or reconstruct the state of any account at any point in time by replaying the events. Cool. When you need to support multiple consumers reading from the same stream. In a real-time chat application, when a user sends a message, it's published to a stream associated with the chat room. This stream acts as a centralized channel where all chat participants are subscribers. As the message is distributed through the stream, okay, this is PubSub. Okay. As the message is distributed through the stream, each participant, consumer, receives the message simultaneously, allowing for real-time communication. This is a great example of the publish-subscribe pattern. Things you should know about streams for your interview. Scaling with partitioning. In order to scale streams, they can be partitioned across multiple servers. Each partition can be processed by a different consumer, allowing for horizontal scaling. Just like databases, you will need to specify a partition key to ensure that related events are stored in the same partition. Multiple consumer groups. Streams can support multiple consumer groups, allowing different consumers to read from the same stream independently. This is useful where you need to process the same data in different ways. For example, in a real-time analytics system, one consumer group might process events to update a dashboard. For example, in a real-time analytics system, one consumer group might process events to update a dashboard, while another group processes the same events to store them in a database for historical analysis. Okay. Replicatie. In order to support fault tolerance, just like databases, okay, streams can replicate data across multiple servers. This ensures that if a server fails, the data can still be read from another server. That's good. Windowing. Streams can support windowing, which is a way of grouping events together based on timer count. This is useful for scenarios where you need to process events in batches, such as calculating an hourly or daily aggregate. A real-time dashboard that shows the mean delivery time per region over the last 24 hours. Yeah. So you got Kafka, Kinesis. I've heard of Kinesis. And Kafka. Yeah, that makes sense. Kafka can be a message queue or a stream, or Kinesis is a fully managed stream service. Distributed log. Redis or Zookeeper. Red lock. Redis based locking. Distributed locks can be used to lock a single resource or a group of resources. For example, you might want to lock a single ticket, or you might want to lock a group of tickets in the stadium. Deadlocks occur when two or more processes are waiting for each other to release a lock. One process requires lock A and then requires lock B, then here discuss how to permit this. Distributed cache. I want to be excited to finish this, dude. So probably take another hour on this. Let me just kind of balance my calendar again. So I also had like a bit of a laundry buffer in here. Excuse me. What have I been doing? What have I been doing the past like few hours? I feel like I just woke up. Like I don't remember what I just did. What have I been doing? No, whenever I fell asleep for like a minute, that just cooked my brain. Large amount of traffic. So the last 30 minutes. Your uploads photos for edit in a real-time chat. I was reading this. I was doing leetcode. Here I was doing leetcode. Well, what have I done, dude? I actually cooked. Doing leetcode here. Leetcode. 2 hours of leetcode. I started reading this. Read this some more. I did my laundry in 8. Did this problem. Went to the bathroom for like 8 minutes. I did another leetcode problem. Looked at my phone and fell asleep for a second. Okay. So, I actually haven't been distracted. I just didn't remember what I was doing. Shit, I already did system design and leetcode. Probably end this 5-hour stream. Do some reading and then do something else. So, give me a eat buffer. Let me finish this. Probably take another 30 minutes. Then I'll read the living room for 30 minutes. Then I'll do gleam depths. I'll read in the living room for an hour. I'll take a walk. All right, 30 minutes. Distributed cache. Oh, almost forgot to change this. Distributed cache. What is a distributed cache and when should you use it? In most system design interviews, you'll be tasked with both scaling your system and lowering system latency. One common way to do this is to use a distributed cache. A cache is just a server or a cluster of servers that stores data in memory. They're great for storing data that's expensive to compute or retrieve from a database. You'll use a cache to save aggregated metrics. Consider an analytics platform that aggregates data from numerous sources to display a dashboard of metrics. The data for these metrics is expensive to compute, so the platform calculates metrics asynchronously, like hourly via background job, and stores the results in a distributed cache. When a user requests a dashboard, the platform can retrieve the data from the cache instead of recomputing and reducing latency. Nice. Reduce number of database queries. In a web application, user sessions are often stored in a distributed cache to reduce the load on the database. This is especially important for systems that need to support a large number of concurrent users. When a user logs in, the system can store their session data in the cache, allowing the system to quickly retrieve the data when the user makes a request. Speed up expensive queries. Some complex queries take a long time to run on a traditional disk-based database. For example, if you have a social media platform like Twitter, you might want to show users a list of posts from people they follow. This is a complex query that requires joining multiple tables and filtering by multiple columns. Running this query on Postgres will take ages. Instead, you can run the query once, store the results in a distributed cache, and then retrieve the results from the cache when a user requests them. Things to know about distributed caches for your interview. Eviction policy. Distributed caches have different eviction policies that determine when items are removed from the cache when the cache is full. Some common eviction policies are least recently used, FIFO, least frequently used. Cache and validation strategy. This is the strategy you will use to ensure that the data in your cache is up to date. For example, if you're designing Ticketmaster and caching popular events, you need to invalidate an event in the cache in the event your database was updated, like the venue changed. Cool. Cache write strategy. This is the strategy that you use to make sure the data is written in your cache in a consistent way. Some strategies are the write through cache, writes data to both the cache and the underlying data store simultaneously, ensures consistency but can be slower for write operations. Write around cache, originally writes to the data store bypassing the cache. It'll minimize cache pollution, but might increase data fetch times in subsequent reads. Excuse me. The write back cache, you write it to the cache and then asynchronously write it to the data store with like a queue. Shout out the cache on your computer right now. This can be faster for write operations, but can lead to data loss if the cache is not persisted to disk. Note, don't forget to be explicit about what data you're storing in the cache, including the data structure you're using. Remember, modern caches have many different data structures you can leverage that are not just simple key value stores. So for example, if you are storing a list of events in your cache, you might want to use a sorted set so that you can easily retrieve the most popular events. Many candidates will just say, I'll store the events in a cache and leave it at that. This is a missed opportunity and may invite follow-up questions. Okay, this is so useful, dude. This is actually wild. What are the two most commonly distributed cache technologies? Memcache. Okay, this is coming back from the book. The two most common in-memory caches are Redis and Memcached. Redis has a key value store that supports many different data structures, including strings, hashes, lists, sets, sorted sets, bitmaps, and hyperlog logs. Hyperlog logs? What is a hyperlog log, bruh? Huh? That's crazy. Memcached is a simple key value store that supports strings and binary objects. CDNs. What is a CDN and when should you use it? Most systems often serve users globally, which makes it challenging to deliver content quickly to users all over the world. Users and interviewers expect fast load times, and delays can lead to poor user experience and loss of traffic. Yeah. A content delivery network is a type of cache that uses distributed servers to deliver content to users based on their geographic location. CDNs, content delivery networks, are often used to deliver static content like images, videos, HTML files. They can also deliver dynamic content like API responses. They work by caching content on servers that are close to users. When a user requests content, the CDN routes the request to the closest server. If the content is cached on that server, the CDN will return the cached content. If not, the CDN will fetch the content from the original server, cache it, and then return it to the user. The most common application of a CDN in an interview is to cache static media assets like images and videos. For example, if you have a social media platform like Instagram, you might use a CDN to cache profile pictures. This would allow you to serve profile pictures quickly to users all over the world. Things you should know about CDNs. CDNs are not just for static assets. While CDNs are often used to cache static images, videos, JavaScript files, they can also be used to cache dynamic content. This is especially useful for content that is accessed frequently but changes infrequently. For example, a blog post that is updated once a day can be cached by a CDN. CDNs can be used to cache API responses. If you have an API that is accessed frequently, you can use a CDN to cache the responses. This can help reduce the load on your servers and improve the performance of your API. Eviction policies. Like other caches, CDNs have eviction policies that determine when cached content is removed. For example, you can set a time to live for cached content, or you can use a cache invalidation mechanism to remove content or from the cache when it changes. Examples of CDNs. Some of the most popular CDNs are Cloudflare, Akamai, and Amazon CloudFront. These CDNs offer a range of features including caching, DDoS protection, and web application firewalls. They also have a global network of edgeless occasions, which means that they can deliver content to users around the world with low latency. Oh my god, I finished it. Wait, yeah, that was just all the comments at the bottom. Common patterns. Oh yeah, I can finish this. This is all comments. Alright, I'm finishing this. And then going to grab my package. By taking these key technologies and concepts and combining them, you can build a wide variety of systems. We've identified a few common patterns that you can use to build systems. These patterns are not mutually exclusive, and you'll often find yourself combining them to build a system. Further examples can be found in our problem guides like Design Ticketmaster, which walk you through an entire system design interview. Simple DB-backed CRUD service with caching. The most common pattern is a simple CRUD service that uses a database for storage and caching to improve performance. This is the pattern you use most for web applications. You'll use a database to store your data and a cache to improve your performance. You'll also use a load balancer to distribute traffic across multiple instances of your service. Many designs will start with this pattern and then add additional complexity as requirements are added. For example, you might start with a simple CRUD service and then add a search index to improve your search performance. Or you might start with a simple CRUD service and then add a queue to handle asynchronous processing. Hint: the design is too simple for all but the most junior roles, but it's a good start. For all levels, we recommend moving quickly in your interview to solve requirements so you can spend ample time optimizing your design and handling deep dives. So pound it out and then move on to the next thing. An async job worker pool. You have a system which needs to handle a lot of processing and can tolerate some delay. You might use an async job worker pool. This pattern is common in systems that need to process a lot of data, like a social network that needs to process a lot of images or videos. You'll use a queue to store jobs and a pool of workers to process them. A popular option for the queue is SQS, and for the workers, you might use a pool of EC2 instances or Lambda functions. SQS guarantees at least once delivery of messages, and the workers will respond back to the queue with heartbeat messages to ensure they are still processing the job. If the worker fails to respond with a heartbeat, the job will be reached at another host. Another example is for your queue to be a log of events coming from something like Kafka. Kafka gives you many of the same guarantees as SQS, but since it's in a pinned-only log, you can replay the log to reprocess events if something goes wrong. Two-stage architecture. Common problem in system design is in scaling an algorithm with poor performance characteristics. Consider the problem of trying to find two images that look about the same. There are many available algorithms that can compare two images and give you a score of how similar they are, but they are wholly inappropriate for a system that needs to compare a large number of images. Even thousands would be too slow. So what can we do? We can use a two-stage architecture. In the first stage, we use a fast algorithm to filter out the vast majority of dissimilar images. In the second stage, we use a slower algorithm to compare the remaining images. This architecture occurs in recommendation systems, search engines, route planning, and many other systems. Event-driven architecture. Event-driven architecture is a design pattern centered around events. This architecture is particularly useful in its systems, where it is crucial to react to changes in real time. Event-driven architecture, EDA, helps in building systems that are highly responsive, scalable, and loosely coupled. The core components of an EDA event-driven architecture are event producers, event routers or brokers, and event consumers. Event producers generate a stream of events which are sent to an event router. The router, such as Kafka or EventBridge, then dispatches these events to appropriate consumers based on the event type or content. Consumers process the events and take necessary actions, which could range from sending notifications to updating databases or triggering other processes. Note: one of the more important design decisions in event-driven architectures is how to handle failures. Technologies like Kafka keep a durable log of their events with configurable retention, which allows processors to pick up where they left off. This can be a double-edged sword. If your system can only process n messages per second, you may quickly find yourself in a situation where you'll take hours or even days to catch back up with a service substantially degraded the entire time. Be careful about where this is used. An example use of event-driven architecture could be an e-commerce system where an event is emitted every time a new order is placed. This event can trigger multiple downstream processes like event processing, inventory management, and notification systems simultaneously. This architectural pattern supports flexibility in system interactions and can easily adapt to changes in processes or business requirements. Additionally, it can significantly enhance the system's ability to handle high loads and facilitate complex workflows. Durable job processing. Some systems need to manage long-running jobs that can take hours or days to complete. For example, a system that needs to process a large amount of data might need to run a job that takes a long time to complete. Okay, if the system crashes, you don't want to lose progress of the job. You also want to be able to scale the job across multiple scenes. Common pattern. Use a log like Kafka to store the jobs. Have a pool of workers that can process the jobs. The workers will periodically checkpoint their progress to the log, and if a worker crashes, another worker can pick up the job where the worker left off. Another option is to use something like Uber's Cadence, more popularly temporal. Warning: setups like this can be difficult to evolve with time. For example, if you want to change the format of a job, you'll need to handle both the old and new formats for a while. proximity-based services. Oh, my neck is clapped. Several systems like Design Uber or Design GoPuff will require you to search for entities by location. Geospatial indexes are the key to efficiently querying and retrieving entities based on geographical proximity. These services often rely on extensions to commodity databases like Postgres with PostGIS extensions, or Redis's geospatial data type, or dedicated solutions with Elasticsearch like Elasticsearch with GeoQueries. Okay. The architecture typically involves dividing the geographical area into manageable regions and indexing entities within these regions. This allows the system to quickly exclude vast areas that don't contain. Quickly exclude vast areas that don't contain the relevant entities, reducing the search space. Hint: while geospatial indexes are great, they're really only necessary when you need to index hundreds or thousands or millions of items. If you need to search through a map of 1,000 items, you're better off scanning all the items than the overhead of a purpose-built indexer service. Note that most systems won't require users to be querying globally. Often, when proximity is involved, it means they're looking for entities locally for them. So I'll save some time to do the common problems and deep dives. So let's see. I'm gonna look at IP for a second to think of how I'm gonna do this. So let's move this up. Let's give me just an hour break here. Then let's do see if I can do the Gleam depths in 3 hours. Eat in 30 minutes. Give me an hour for the Kate's book. Give me an hour for systems design in a hurry. I'll do an hour 15 more of this, and I'll set a goal to so which ones do I think are particularly useful here? So I want to do hello. Do the hello int. I'll do the deep dives for Redis. Redis deep dive. I think that's particularly useful. And well, it looks a low level here. I'll do the Dropbox con problem. Hello int Dropbox. So I'll do those later. Then probably tomorrow, try to do the hello int. I'll look at Kafka. DD. And I'll look at the leetcode. Hello int leetcode. So, yep. And in this pretty good morning so far. I did like 2 hours of work. I expect to do like 8 hours a day. I did like 2 hours of work this morning, and then streamed for about 5 hours, so 7 hours. So one more hour.